Previously, I showed you recurrence relations, but what I did was I showed you a pretty easy formula. But what if the formula is frankly more complex and not easy to exactly, guess where the next value is? This is just another way of finding the next value in sequence. You know that part already. But pretend this is going to use a random equation that frankly is just a heck of a lot more complicated than what you and I were expecting. Again, it's still going to need one or more of the previous terms in the sequence, just like this one does. This one's going to need the value before a of n, and this one's going to need the value that was two values before a of n. So things will get pretty interesting with this pretty quickly. So you need that previous previous values or knowledge in order to complete the work. This can be dangerous, so just a heads up on that. But here's the thing, you're given initial conditions. This is something you haven't seen before, is you're given two values already, normally we're just given one, and we're given some type of, parameter on exactly where to start with our n when it comes to the rest of our equations that we have here. So if you look at the recurrence relation that we have here, we have our equation, and then we have our initial conditions, which is both of our for and our where that are frankly right there written in front of you. Now, how's this going to work out? Well, first of all, let's go ahead and write down our two items that were already given. A of sub 0 and then A of 1, both 2 and 5, and again, already given. Now we use the equation. We got to say, okay, what's A of the n minus 1, which is right now we're at A of 2, so that's 2 minus 1 is 1. And then we're going to have 2 times A sub 0 because it's going to be 2 minus 2. That'll give us 5 plus 2 times 2, and then 5 plus 4 is equal to 9. Notice we'll continue that pattern, but we'll keep shifting up on the next value that's supposed to be in our overall scheme because A sub 0 is 2, A of 1 is 5, and now we found out that A of 2 is equal to 9. So A of 2, there's a 9 being used right off the bat, and then we're going to have our 2 times A of 1, which is 5. That was the previous one in order. So notice how it's relying on literally previous right work in order to do its job. That's a recurrence relationship when, again, you might have a much more complex function that you really need. That's why you might need the recurrence in order to do the work that you need. Here's a couple of examples. So I want you to find, or let A be the sequence that satisfies the recurrence relation. So we're given a formula or some type of function. We're given some type of, conditional. And now I'm asked, given a starting point, which is A naught or A of 0, A naught, find A1, 2, and of 3 respectively. Now, just like we did before with the recurrence, I need to use the previous answer to help me with my current one. Same exact idea as what I have here. So I'm first given A of 0, which is equal to 3. I'm going to need that in order to get A of 1 because remember in the equation, A of 1 is equal to 1 minus 1, which gives me 0. So there's the A of 0 plus our 6 equals, we do that from there on out. 3 plus 6 equals equal to 9. Equal. Ooh, interesting. But anyway, so there's our 9. So we have an answer now for A sub 1, which I'm then going to end up using here because I need it for the next part of the equation. And notice how it builds off of one another. Notice, by the way, there's a common difference between all of those of plus 6. Common difference, huh? Anyway, we're going to try it again. Same exact idea, but our starting point is slightly different. This time it's negative 7. You know what I'm going to do. I'm going to end up using that negative 7 because it's going to look for that first one. A of 1 is equal A of 1 minus 1, equals 0 plus 6. There comes my previous answer that I had needed before, and you'll see it show up again once I get the negative 1. I need that negative 1 before that. Overall, same set of needing that previous answer in order to fulfill its current job. And again, notice, by the way, common differences, plus 6 for each of those. Now, wait a minute. Wait, there's more. So if we have a common difference for these two equations, and I'm given a starting point for both of those, can't I make that into arithmetic sequence? And the answer is yeah, for exactly what I was talking about. Now, we'd have two separate answers for this. The first one being A would be A of n equals 3 because that was our initial starting point plus 6n. Now try it out. I had to double check myself there for a moment. So if we tried this out for A of 1, it would end up being 9. For A of 2, be 15. Using this equation here, A of 3 equals 21. So you can double check this if you want to, but it happens to work out. Kind of, yeah, hey, cool. Same thing for B, but notice again, the overall back end is the same, but the initial starting position is not. So these are considered two different equations, even though both of them are arithmetic sequences. They started at different positions. So that's how we can get away with, if it happens to have a common difference somewhere, or maybe a common ratio, then we can use some of the other known sequences that you and I have done before, and we can translate it into those.